First point is, what is stereochemistry? So there are many definitions of stereochemistry. So you can see here, this is made up of Greek word isos plus meros. Isos means equal, meros means part. That is called isomerism. This is coined by Bergelius. So first term is isomerism. So initially there was isomerism. People were not knowing about the stereoisomer. So first this we started with the isomerism. Means different compounds having the same elemental composition, pair of compounds having similar molecular formula but different structural formula. So they have different physical and chemical properties. So they are called isomers. For example, ethyl alcohol and dimethyl ether. This is the first example we are knowing since class 11th or 12th, like that. So now we can see here type of isomerism: structural or constitutional isomerism and stereoisomerism. Stereoisomerism means simply the different isomers having same bonding structural formula but different stereochemistry of the compound. That is stereoisomerism. And structural constitutional isomerism are, these are different types: chain, skeleton, position, functional, metamerism, tautomerism, ring chain isomerism. This you are knowing since beginning. And stereoisomerism can be classified in configurational stereoisomerism and conformational. So configurational isomerism again can be classified geometrical isomerism and optical isomerism. Conformational can be divided into rotational and inversion. These are the different structural, no need to discuss here. Chain, position, functional, metamerism, tautomerism. This is example of chain and butane, 2-methyl propane, like this. This is another example of chain isomerism. You can see orthodichloro, metadichloro, paradichloro. Okay, this is functional isomerism, ethanol and ether, acid and ester. Okay, this is metamerism, where what is the difference here? Simply number of carbon atom in alkyl will be different. So this is the same kind of molecule, means having different alkyl formula. So that is metamerism. Tautomerism having interconvertible functional groups. So these are some examples of this one. See, encyclopropane, this is ring chain. Okay, this is no need to discuss. Now we will come directly on stereoisomerism. That was just a glimpse of, to recall your memory. That's why I started from there. So stereoisomerism, isomers which have the same formula as I told, but differ in manner of their atoms and groups are arranged in the space, are called stereoisomer. It is two types: configurational, conformational isomerism. Configurational isomerism, which cannot be interconverted without making and breaking the bond, are called configurational isomerism. These isomers can be separated under normal condition. These are also two types: optical isomerism or enantiomerism, and second is geometrical isomerism. Optical isomerism, which are related to each other as an object and its non-superimposable mirror image, are called optical isomers or enantiomers. So in enantiomer, there is another definition. You can define in another way also. The isomer and its mirror image, which are not non-superimposable, are enantiomer. Okay, they are called enantiomer. And optical isomers can also rotate the plane of polarized light to equal degree, but in opposite direction. Then they are enantiomer. And this rotation of plane polarized light is known as optical activity. So the optical isomer have similar physical and chemical property. What is the difference? Difference is in their optical activity. For example, we can see here two enantiomers, lactic acid, minus and plus. This will rotate plane polarized to left side, that is minus. Plane polarized to right side is plus. These two are mirror image of each other. Geometrical isomerism are stereoisomer which differ in their spatial geometry due to restricted rotation across a double bond. For example, you can see cis and trans isomer. Now conformational isomer. The stereoisomer which can be interconverted rapidly at room rotation of the bond are called conformational isomerism. Because such isomers can be readily interconverted, they cannot be separated under normal condition. So two types of conformational isomerism are there. One is conformational isomer resulting from rotation about single bond, and other one is conformational isomer arising from amine inversion. You can see conformational isomerism resulting from rotation about single bond. You can see chair form is converting into board form in cyclohexane. So this is simply rotation of a covalent bond. Okay, this is called conformational isomer. They are interconvertible at room temperature. When you will heat, then that conversion will be fast. Another one is this is amine conformational isomerism arising from amine inversion. What is this? Here, nitrogen atom of amine has a pair of non-bonding electrons. That's why this is asymmetric. Four different groups are here. Three alkyl group and one lone pair. Okay. So this non-bonding electron which allow the molecule to turn inside out rapidly at room temperature. This is called amine inversion or Walden inversion. So you can see here transition state how this inversion takes place. That lone pair is first if in first structure it is exposed outside, then in second structure that is inside. That's why it is called inside out. Now optical activity. Enantiomers are known to possess same physical and chemical property, but they differ in the way they interact with plane polarized light. So substances which can rotate plane polarized light are said to be optically active. These are two types, dextrorotatory and levorotatory. This is made up of Latin word dextra means right and it is indicated by plus sign. And levorotatory made up of levers. Levers plus rotatory. Levers means left and it is indicated by minus sign. Okay? And if any substance which cannot rotate the plane polarized light are called optically inactive. A small d, old convention, rotate the plane polarized to the light. In the same way, levorotatory minus and a small l. Okay? What is plane polarized light? You know, light can vibrate in all directions. Okay? If you will see exactly, light will be like this. All direction, this is unpolarized beam of light. When you will pass this, the polarizer, okay, then polarizer is having only single window, slit window here. So only one of the vibrational direction, one of the plane of the light will pass through the polarizer. So you will get plane polarized light like this. Now this will pass through the sample, through material to see the optical activity. For example, here incident polarized light only one direction means it is polarized light. When it will pass through the sample, this is a sample cell where sample is kept inside this cell, and after passing through this, the direction of the this plane polarized light will change in transmitted light. So this way we can examine the optical activity of the material. What is polarimeter? Here, the sodium lamp is used to give the light. Then polarizer is there, which will create plane polarized light. Then sample cell is there. Then after analyzer is there, from where you can analyze the rotation of the plane polarized light. So overall, this is called polarimeter. An angle of rotation is the angle by which analyzer is rotated to get the maximum intensity of light. How it will be affected? It depends on nature of substance, concentration of the solution, length of the polarimeter, and wavelength of the monochromatic light, and temperature of the sample. And there is one term is there, specific rotation. Specificity gives usually for any in any kind of definition. If a specific term is there, so there is unit parameter that will be used. For example, in this case, the number of degree of rotation caused by a solution of 1 gram of compound per ml means 1 gram sample in 1 ml will be used as a solution. Then what will be the rotation of plane polarized light at that particular temperature, and length of the tube is 10 centimeter. Then polarization, then rotation is equal to specific rotation. It is represented with alpha lambda T naught. Where alpha lambda T naught, here alpha is, this is specific rotation, and T naught is the temperature of the sample, lambda is the wavelength of incident light. Okay. Now specific rotation. So alpha dt is equal to alpha by Cl. Here d is yellow light from sodium lamp. Alpha is the observed rotation, C is the concentration, R is the length of cell, T is the temperature. This equation is used to calculate the rotation using a specific rotation constant. But what is molecular rotation? Molecular rotation which is preferred over specific rotation, which is given by this formula. You can simply change the equation, then you will get molecular formula. Simply, if rotation by a molecule is molecular rotation, simple definition. Now we will see chirality, optical activity. So how it was discovered? First time it was discovered by Pasteur in 19th century. They have seen the crystalline optically inactive sodium ammonium tartrate was in a mixture of two types of crystals, which were mirror image of each other. Each type of crystals, when dissolved in water, was optically active. The specific rotation of the two solutions were exactly equal but of opposite sign. In all other properties, the two substances were identical. As the rotation differ from the two sample in solution in which shapes of crystal disappear, Pasteur laid the foundation of stereochemistry. when he proposed that, like the two sets of crystal, the molecules making up a crystal were themselves mirror image of each other, and the difference in rotation was due to the molecular disymmetry. How he discovered tartaric acid? He used to prepare sodium ammonium tartrate. This was that crystal which becomes source of the invention of stereochemistry. These are two crystals, sodium ammonium tartrate. He found these two crystals are mirror image of each other. They have similar structure, but they are mirror image of each other. Chirality, an object which cannot be superimposed on its mirror image is said to be chiral, and the property of non-superimposability is called chirality. For example, in this figure, you can see our hands. Chiral objects, human hand, gloves, shoes, etc. Achiral objects, a sphere, a cube, a button, socks without thumb. Chirality or molecular disymmetry is a necessary and sufficient condition for optical activity. Chirality in molecule is usually due to the presence of sp3 carbon atom with four different groups attached to it. Such a carbon atom is called chiral carbon or chirality center. The presence of chirality center usually leads to molecular chirality. Such a molecule has no plane of symmetry and exists as a pair of enantiomers. Such a carbon atom is sometimes also referred to as asymmetric carbon atom. Here you can see one example, derivative of methane. Four different groups are there. If you see the mirror plane of each other, this molecule, and anyhow, if you will try to superimpose this by any rotation without breaking the bond, they are not superimposed. So these two are enantiomers. You can see here again. This is the one crystal we have seen, sodium tartrate crystal, that one, and this is the mirror image of that one. For example, if this will exist like this, okay, then these two are mirror image, but these two are non-superimposable. Pasteur hypothesis usually lead to the discovery of tetravalent carbon atoms or tetrahedral. Only tetrahedral geometry can lead to mirror image molecules. Square planar, square pyramidal, and trigonal pyramidal will not work. So this is the foundation of tetrahedral carbon also. Here in enantiomer, you can see one is dextrorotatory, one is levorotatory, and they are mirror image of each other. How to distinguish enantiomers? Here you can see in Fisher projection it is drawn in first figure here. This is mirror image of each other. So two horizontal bonds are there, CY and CW, and two vertical bond is there, CX and CZ. The superimposability of these two flat two-dimensional structure is tested by rotation in twin without raising them. A symmetric carbon atom is at the junction of the cross line, means carbon. Some examples you can see here. Glyceraldehyde is here. This is, you can see the mirror image of glyceraldehyde. You can see the mirror image of lactic acid. acid again you can see here. Symmetric carbons are there. Two asymmetric is carbons are here. So you can see this is optically active or not. So this is a very good example. One is showing plus tartaric acid, which is written, another one is minus, and third one is mesotartaric acid. This is there is a mirror plane in between the molecule. So one, if one is R configuration, one carbon is there, another carbon is yes. But in these two cases, they are not. There is no mirror plane in between the molecule. You can see. So both carbon having same configuration. That's why these are either plus or minus. But in this case, it is this molecule is optically inactive. What is inversion of configuration? The enantiomer is changed into another when two atoms or groups about the chiral carbon are interchanged. Then it is called inversion of configuration. So if 90-degree rotation of the projection formula about the chiral center or one exchange of groups invert the configuration of the original structure. And if two such exchange will be there, you will get same configuration. Means once you rotated, then configuration is just inverted. Again you rotated, then you will get same configuration. You can see here in this example, here this is plus, this is minus, this is again plus. So what is done here? This is rotated here, okay, this way, and then CHO, CH2OH, H, OH. Okay. So if it is rotated here, OH will come here, CH2OH is here, H is here, okay, and CHO is here in this rotation. Then if you rotated all the groups one time, 90-degree, you will get this one, that is minus. Again you rotate, okay, then you will get plus. So that was the meaning of last statement. If you will rotate 90-degree, you will get opposite configuration. Then again, if you rotate 90-degree, you will get same configuration. Okay. These are the different projection formula. How to represent the molecule in three-dimensional structure. So there are four different types: Fisher projection, Newman projection, Saha's formula, and flying wave formula. You should know, you are knowing, I think. Only I will give a rough, I will give a small glimpses of this projection. You just see and you just recall your uh, information from your brain. For example, this is Fisher projection. How it is represented? Three-dimensional structure into two-dimensional structure. So you can see CH and COH is in horizontal line, and OH, COH, and CH2H is in vertical line. All groups are here. So rotation of a Fisher projection by an angle of 180 about the axis, which is perpendicular to the plane of the paper, gives identical structure. We have seen earlier in previous example. Now you can see Newman projection. Newman projection is the molecule. We look at the molecule down the length of the particular carbon-carbon bond. Means our eye is on that carbon-carbon bond, vertical, that exactly above that or below that. So it will be like this, round. This is the vertical carbon-carbon bond. So this is the front carbon and this is the rear carbon. When you will club these two, you will get this is Newman projection. And different substituents we can put here. And this is staggered conformation when biggest group are just empty to each other. Eclipsed when biggest groups are just overlapping to each other. Okay. And another one is Gauche, that is in between these two. Sahar's projection. The bond between two carbon atoms is shown by a longer diagonal line because the two are looking at this bond from an oblique angle. The bond linking other substituent to this carbon are shown projecting above or below this line. So you can see how it can be shown. If this is staggered, you just bring this carbon to here, then you will get staggered. And you just slightly shift that bond here. Earlier in Newman projection, this carbon-carbon bond was vertical, and you cannot see this one. Only you are looking this point. Now it was tilted little bit, and you got this stagger in Saha's projection. The same way eclipsed one also. Now this is flying wedge. This is exactly three-dimensional representation. The flying wedge formula of two in instrument like this are shown here. You can see both are mirror image of each other here. Means exactly this is the method to represent the molecule in three-dimensional geometry. Now how to convert this interconversion of this? This is Fisher projection. This is Sahar's. Okay. So how you can convert C2 and C3? You have to concentrate. Your target is these two carbons. These two carbons you just put here a diagonal line. Then now first concentrate this carbon. Three groups are there: COH, OH. COH is just above. So COH you will put a vertical line above, and H is left. So you will make a bond here H, and this side OH. In the same way, this carbon also. This OH is H is there. H is right side. This OH is left side, and this COH will be always up. Okay, this is eclipsed conformation. From Fisher projection, you can exactly get eclipsed conformation. So that's why you are getting this one. You can rotate this one and you can get a staggered one. How you will rotate? You will fix one side, you will rotate another side, then you will get staggered conformation. This is Sahar's projection. Now again from Sahar's to Fisher projection, how you will do? If that is staggered, first you convert into eclipsed. You simply bring this CS3 up. This will be here. This will be here like this. Now you will simply convert into the Fisher projection. Carbon-carbon bond. This is this one, and this is again straight. This CS3, CCS3 is again below, and you can make like this. That is Fisher projection. This conversion of Saha's projection to Newman projection. Then here you can see staggered conformation. Simply you bring this carbon and put it here, and you will get the Newman projection. Here in the same way, this one Fisher projection. This is always Fisher projection is representing the eclipsed conformation. So eclipsed. So how you can get eclipsed? These two are carbons are the vertical carbon. You put it here. Then this is front carbon. This is rear carbon. Front carbon you just draw exactly like this on this carbon. So this is phenyl group which is below. This is bromide group. This is right. This is OH to left. Then CS3, Cl, and NS2. So it is very easy to convert this one into this. And from here to here, this is staggered conformation. You can easily convert into eclipse. You just rotate this carbon-carbon bond in such a way that bigger group will so could come on in just above the bigger group. So PS3 phenyl group is the bigger group in this front carbon, and rear side CS3 is the bigger group. So PS3 will you have to bring PS3 just above CS3. So you will rotate here 180. This will also you rotate 180. This will also you rotate 180. So all will overlap to each other. Then you will get eclipse Newman projection. Conversion of Fisher to Sahar's projection. You can see here also. This is Fisher projection. This is eclipsed. So eclipse to eclipse. First, this is a front carbon. This is rear carbon. Okay, you can easily convert. You do some practice. After practice, you will get. There is no problem. Okay. Now this Fisher projection, how you can convert into flying waves? You just simply take this example here. When bromine is above the plane, okay, in this case, and in another case when hydrogen is above the plane, it was drawn like that. So in this molecule, you are looking from this side, okay. So COH and CS3, these and this carbon, these are in one plane. So it will look like this. Then now you can see if this will like this, then where will be hydrogen, where will be bromine? If you are looking from this side, then bromine is towards you and hydrogen is away from you. Okay, then bromine will be with solid line and hydrogen will be with dotted line. And if reverse is there, you are looking from this side. Okay, so this bond you will see like this: COH, SE, and CS3, and hydrogen will be towards you. Bromine is away from you, so hydrogen will be with dotted line. Now conversion of flying waves to Fisher into Fisher, you can see simply you are looking from this side, for example. So if you are looking from this side, so COH is up, CS3 is below, and bromine is towards you. So bromine is right side and hydrogen is this side. So this way we can interconvert. These are different elements of symmetry. Group theory, it will be discussed in group theory. Okay, this is plane of symmetry. This is an imaginary plane in mesoisomers, which divides a molecule in exactly two equal parts, and both parts are mirror image of each other. You can see here mesotartric acid is one of the good example. Now these are different symmetry elements, center of symmetry, and all. Okay, no need to discuss. Now asymmetry and disymmetry. In general term, asymmetry is used for those atomically active compounds which have none of the four elements of symmetry. Means all four groups are different. Then it is called asymmetry. Now, in contrast, the term disymmetry is used for all stereoisomeric compounds which are capable of existing as pairs of non-superimposable mirror images despite the presence symmetry. So these are called disymmetry. In other words, the disymmetry is applicable to all stereoisomer which are related to each other as non-superimposable mirror images. Means any molecule is not superimposable to each other, it means that is having disymmetry. Simple meaning. Here we can see some examples. Here this is first, second, and third. Three structures are there. So in this we can see the molecule has C2 axis of symmetry, but it is not superimposable on its mirror. C2 symmetry you are knowing, there is one axis, you will rotate that by 180 degree, you will get the same molecule. So this is C2 axis of symmetry. And this one rotate 180 degree, then you will get this one, second one. So all asymmetric molecules are disymmetric, but all disymmetric molecules are not asymmetric. This is very important. Both these types of molecules are optically active and are chiral. This is also true. Stereogenic center or chirality center. What is this? In last of 20th century, it was suggested that tetrahedral carbon atom bearing four different atom circles may be called a chirality center. Several earlier terms, including asymmetric center, asymmetric carbon chiral center, stereogenic center, stereo center, are still widely used. Characteristics of enantiomer. What is the characteristics of enantiomer? Molecule should be chiral or disymmetric. The molecule and its mirror image should be non-superimposable, even if it may not have an asymmetric carbon or stereo center. In general, it is observed that chirality centers shows enantiomerism, and therefore they are rapidly active. Compounds having chirality center but non-enantiomeric. Mesoisomer simply you can say compounds with chirality center but are enantiomeric. Okay, so today we will stop here. Again, we will start tomorrow, same time. Okay, all of you, we will start here at tropoisomerism of biphenyls like that. Alene and related items we will discuss from here. Okay, non-superimposable mirror images and enantiomeric and apically activity of this kind of molecules. There is no chiral center but are enantiomeric. You can see here there is no carbon where four different means you can say that is asymmetric kind of thing. So we will discuss tomorrow from here. Okay. Now it is 2 o'clock. So you